Hello, calculus people. So like the video said, I just want to show you the algebraic limits that you've already done before, just so we're clear on the limits you've done before, and then we're going to talk about the limits that we haven't done before, the more advanced ones. So under the class term on important documents you'll need all year, finding limits algebraically. So this is a really good roadmap to have all year. I just want to remind you, I know I've shown you this before, but just so you know, these are the types of algebraic limits you'll need to know for the entire year. Limits going to infinity with the horizontal asymptotes, limits going to a number, sometimes that's a vertical asymptote, sometimes direct substitution works. Sometimes you get 0 over 0, which means you have a whole. So again, always remember the stuff you already know. We did graphical limits. Those are probably the easiest limits that we've done so far. And now we're going to talk about more advanced types of limits. So when we get to the more advanced types of limits, we're going to start seeing some properties of limits that are in pretty much every calculus book that you're going to pick up. So what I want you to do is pause the video and write these down here. I know there's a lot and it's kind of a pain in the butt to write it down, but it's good to have and you're going to need it. One thing I want to point out is that all these limit properties only work under the assumption that the limits as you approach C for F and as you approach C for G exist, meaning that neither of these limits is D and E. So these are limit properties are great to know. They're kind of intuitive, like the way you say is the limit of a sum is the sum of two limits, or the limit of a difference is the difference of two limits. Like that kind of makes sense. You've done stuff like that in math before. The only one that might not be immediately obvious is the composites one, and that's the one that this video is actually going to focus on a lot because composite limits are something that were added kind of recently. They started asking these questions more and more starting in 2017. So I want to make sure we're aware of how to do those. And that is if you have f of g of x, then you start on the inside and you find the limit as you approach g of x, and then you input that into the outside function f. Okay, so that's all fine, but what the video is mainly going to focus on is if what happens when you try to use these nice rules, but one of the limits does not exist. Now, AP has started asking this more frequently because they realize that students were just blindly applying these rules here, and they don't want students blindly applying rules. They're always trying to get you thinking. They're always coming up with new problems. So what we're going to talk about mainly today is, let's say you try and use one of these rules, but one of the limits doesn't exist. Then what? So the main thing we're going to be doing today is, for composites especially, if one of those limits does not exist, mainly because the function isn't continuous, like if there's a piecewise function or a jump discontinuity, then we're going to have to go back to basics. And back to basics means, how did we first start defining limits? And we defined limits with one-sided limits, meaning if the limit from the left equaled the limit from the right, then the overall limit was the same. And another way that we started with limits is numerically, where we plugged in values really close and saw what the y value approached. That's going to be our main toolbox whenever these nice algebraic properties don't work. Now, sometimes these do work, so I don't want you to think you can never use these, or else I wouldn't even show them to you. They work a lot of the times, but we're going to talk about what happens when they don't work. So let's start off with this example here. I have what looks like to be two parabolas and a line. I have a jump discontinuity at 2, and I want a composition, a limit of a composition, f of x. Now this graph is the function f, so it's not like you have f of g of x and there's two different graphs. You're looking at the same graph here. So I'm going to try and apply the rule here. So what it would say is the outside function and the inside function. You start on the inside, you find that limit, you evaluate the outside function at whatever the inside limit was. So let's try it. So I would have f of the limit as x approaches -2 of f of x equals, so again, here's my outside f, here's my inside function f. I'm highlighting because since both of them are called f, it can be confusing to see which one's the outside, which one's the inside. So the limit as x approaches -2 of f of x, well, that is definitely 2. So this right here is 2. Now I'm going to do f of 2. So if I go to f of 2, two things are going to happen here. About half the people are going to look at this and say, all right, the function value at 2 is 4. And then maybe some other people, another half of people will look at this and say, all right, well, I am finding a limit here, and at 2, I don't really have a limit because of this jump discontinuity. So another group of people is going to say it does not exist. And you know what? The thing is, both of those groups of people are wrong. And the first time I ever saw this limit myself, I thought 4 because I just applied the limit rule. I had never seen one where there was a jump discontinuity there. That was a new type of problem. I myself had never seen it when I took calculus in college. So here's the key idea for how we're going to handle this. And I find that remembering this key idea helped me not to make that mistake. When we're doing composite limits of this type where one of the limits does not exist, then what you're doing is you're finding a limit twice. You are not going to evaluate the outer function at the answer to the inside limit, which is exactly what I did do here. I tried evaluating the outer function at whatever the limit was, which was 2. So you can't do that whenever you have a jump discontinuity and one of the function is not continuous. So here's the key idea. And we're going to go over this several times so that you remember it. For composite limits, whatever your answer is for the first limit, the inside one, whatever your output is, that's going to become the input for the second limit. So I'm going to do 2 limits. And input means whatever x approaches. So let's go ahead and actually try one. And I'm going to show you the way you're going to want to approach this. So we're going to break it down into our fundamental understanding of limits. We're going back to basics here, people, because the answer is neither 4 nor does not exist. So here's how you get the actual answer. So we're going to forget about this rule here. It doesn't work because our function is not continuous. Our outer function f is not continuous. So I'm going to do a left-hand limit and a right-hand limit. So let's start with the left-hand limit first. And we are still going to start on the inside here. I'm going to do the limit as x approaches f of x, the inside one. So again, I'm doing yellow here. The limit as x approaches -2 from the left of f of x. So we're not even looking at the blue outside one yet. We're just focusing on the inside one. So the limit as x approaches -2 from the left. Well, the limit is definitely 2 for this one-sided limit, but what I'm going to do is put a minus after, and this is really the key to this. The reason I'm putting a minus after is because as I approach -2 from the left on my graph, the way in which I am approaching the y value of 2 is with y values that are less than 2. So I'm approaching 2 from values smaller than 2, like 1.9, 1.99, 1.999, etc. Let's try from this side. The limit as x approaches -2 from the right. I'm going to start on the inside function, just like I normally would with a composition or a composite function. I'm approaching -2 from the right, so coming this way. Jump on the graph. I'm approaching -2 from the right. What are my y values doing? Well, okay, obviously the y values are approaching 2 again. And again, I am approaching the y value of 2 from y values that are less than 2. So I'm going to put a negative there. I'm coming from underneath 2. So I'm kind of making it look like a one-sided limit here. So now what we're going to do is we're going to go to the outside function. And the outside function was f of x. So here I am. That was this outside function. And whatever the output was for my first becomes the input for my second. All right, so now I'm on my outside function, f of x. I'm now going to approach 2 from the left. So whenever I put 2 minus here, that meant I'm approaching the y value of 2 from underneath, from y values left of 2. Now, when I turn it into another limit, this means 2 from the left, the way you've always known 2 minus to mean. So here's 2 from the left. I'm approaching 2, and that limit is 2. Okay, let's see if I get the same thing here. I'm going to do the limit. Oops, that should be great. The limit as x approaches. And first of all, this f of x is my outside one. And it's 2 minus, that was the output of the first one, that's going to become the input for the second one. So notice, even though the left and the right hand limits started differently, left and right, they ended up the same. Either way, I'm approaching 2 from values that are less than 2, from the underneath side of 2, from the left of 2. So as I approach 2 from the left, the limit is 2. And because the left and the right hand limits are the same, overall the limit of the composition is 2. And another way you can think of this, because sometimes people view this as the limit of 2 different functions, and you don't want to think of it like that. This is really the limit of f of x, which is its own function. So this is the function f. The function f of x is a different function. So what you can do is actually graph what the composition is. I don't know what these exact equations are, but if you did know what those exact equations are, you could actually graph f of x. And I actually have a visual here, what f of x looked like. And remember, we're doing the limit as x approaches -2. Whoops. Okay, so here's f of x. Here's -2. And as you can see, as I'm approaching -2, the limit is definitely 2. Notice the composition looks really similar to the actual function f of x itself, but it is a little bit different. So when you look at the actual composition, you can see our answer is right. The limit is 2. Now let's confirm it numerically. Now you might be thinking, all right, I believe you. Let's not do more work for this problem. But I think seeing it numerically just one time is really going to help you visualize what's actually happening here. So let's forget about the limit rule here. It doesn't apply anyway. And let's pretend that we don't really know what to do for the limit of a composition. So we were just going to do what we did at the beginning. We plug in numbers really close to -2. So this would be f of -2.1. Okay, so start on the inside. F of -2.1 is somewhere around there. And I'm going to estimate this to be like 1.9. So now I'm going to do f of 1.9. So I'm at 1.9. And I'm going to estimate that to be around 1.9. Okay, now let's do f of -2.01, getting closer. So -2.01, let's say, is like right there. When I go up, I'm really close to 2. I'm like 1.99. That's an estimate. F of 1.99. Okay, let's go to 1.99 and go up. I'm really close to the y value of 2. I'm going to call that 1.99. Okay, now let's go from the other side. F of -1.99. So here's -1.99. I'm super close to -2. I'm going up. I'm going to estimate that to be a y value of like 1.99. So notice, even though I am starting on the other side, I end up approaching 2 from the left again. So f of 1.99, here we are again. We've been here before. F of 1.99 was 1.99. And last one, f of -1.9. Okay, f of -1.9 would be around here. I'm going to estimate that y value to be like 1.9. And f of 1.9, here we are again. I'm on the left side of 2, just like I was approaching 2 from the underside here. I'm going to estimate that. I already did that to be like 1.9. So you can see coming from the left and coming from the right, we are approaching 2 no matter what. Okay, so that's our first example here. Let's try another example. If you want a little summary, some people like to write steps down just to refer to the way you do a composite limit when you can't apply this rule. So this is for when you can't apply that nice rule. You're going to do the limit from both sides. You're going to go back to basics, left hand and right hand limits. And you're going to still start on your inside function. Then you're going to go to the outer function, and whatever the previous limit's output was will become your new limit's input. So here's where you put your output. Okay, so now you're going to find your new limit. So notice you are finding a limit 2 times. Limit and limit. If you didn't do a limit twice, you didn't do the problem correctly. So pause that and jot that down. It might help you in case when you look at your work later, you're wondering what actually happened. Okay, here's a nice multiple choice. So I'm looking for the limit as x approaches -1 of f of x. So let's go ahead and try to apply our rule here. And our rule said that the limit as x approaches c of f of g of x equals f of the limit as x approaches c of g of x. Okay, so that would be the limit as x approaches -1 of my inside f of x. We'll call this my outside. And the limit as x approaches -1 is in fact 3. Then I'm going to do the outside. So then I would do f of 3. Okay, well, I'm at 3. And remember, if your outside function is discontinuous at the value, then you can't apply this rule. And look, f of 3, I definitely have a jump discontinuity. You might think it's 1/2 if you forget that the rule doesn't apply. Some people might say, oh, it doesn't exist because there's a jump discontinuity there. But neither of those answers is correct. So let's find out what the answer actually is. So that's not correct, and let's do it the right way. So I'm going to do the limit as x approaches -1 from the left, and the limit as x approaches -1 from the right. So the more of these we do, the quicker they will become. The first one took a while because we broke it way down. They really don't take that long. So I'm going to go from the left first, and then we'll go from the right. Starting on the left, I have my inside function, f of x. I'm ignoring my outside function for now. Okay, the limit as x approaches -1 from the left. All right, that's definitely 3. And I'm approaching 3 from the underneath side, from values that are less than 3, 2.9, 2.99, etc. So I'm going to put a negative there. So then I'm going to do the limit as x approaches 3 from the left. And now I'm going to go to my outside function, which was f of x again. So now let's approach 3 from the left. And you can see your limit is -1. Let's see if the right-hand limit matches. If so, then our overall limit of the composition will exist. Okay, so I have the limit as x approaches -1 from the right of f of x. And this is our inside function, f of x. So let's approach -1 from the right. I'm clearly getting close to 3. And again, I'm approaching 3 from values that are less than 3. So I'm going to put a negative there. And notice I immediately end up with the same exact thing. This is still going to be 3 from the left of my outside function, f of x. I already did that. I got -1. So sometimes when you do this, they will end up being the same thing in the end. So your overall limit is -1 because the left and the right hand limits were the same. So you can see that the rule definitely didn't work. We didn't get 1/2, or it does not exist. Okay, let's try this one. So if I try to apply the rule, I'm going to show you one more time why we can't apply the rule. Let's set up the rule here. This is what the rule would look like if I tried to apply my composition rule. There we go. So this would be f of, now the limit as x approaches 0. That's definitely 2. And then if I try and do f of 2, there's that jump discontinuity at the outside function. Some people might guess 1, some people might guess does not exist. These both will end up not being correct. So we don't want either of those. So let's go ahead and see what the answer actually is. Break it down, left and right hand limits. So 0 from the left and 0 from the right. Okay, so you've seen me do a couple problems. I want you to try this right now, and let's see what happens. So pause the video and give this a try, and then I will quickly go through it. Okay, people, so hopefully you gave this a try and you did it all the way out. Hopefully you ended up with 0. If so, nice job. If not, let's see what happens. Did you start on the inside from the left and the right? Did you say 2 with a minus after because you're approaching 2 from values less than 2? And then did you approach 2 from the left and you get 0? All right, pause that if you need to. If not, let's try another one that's really similar. Now I want you to look at this graph and this graph. They are the exact same, except I'm going to take this piece and reflect it over the line y equals 2, so it turns into this upper arc right there. So we're going to find the limit as x approaches 0, and I'm going to end on this example because it is a little bit different, and I like this problem a lot. If I try the limit rules, it's not going to work. Hold on, sorry. All right, so I tried doing our limit rule that was on page 1 of the video, and you can see if I do the inside limit, I get 2. But then if I do f of 2, the outer limit doesn't, I'm sorry, that function has a discontinuity when I evaluate my outer function. It's a jump. Some people might guess it's 1 and say, oh, well, f of 2 is 1, but you can't use this rule if the function has a discontinuity on the outside, if that limit doesn't exist. Okay, so let's break it down into basics. Limit from the left as I approach 0 and limit from the right as I approach 0. I'm going to start on the inside like I always do, and I'm talking this one through because something interesting is going to happen here. As I approach 0 from the left, now watch carefully what happens here. Approaching 0 from the left, I have a limit of 2, and I'm going to put a minus because I'm coming from values that are less than 2. Here, if I do the limit from the right, as I approach 0 from the right, I am still approaching, 2, but from values bigger than 2, like 2.1, 2.01, 2.001, etc. So I'm going to put a plus sign. This was the function f of x. So this time, when I go to my outer function, I'm going to go 2 from the left. Whereas here, when I go to my outer function, I'll be approaching 2 from the right, because the output here was 2 negative, so the input here is 2 negative. The output here was 2 positive, so the input here will be 2 positive. So here's my outside function, which was green. As I approach 2 from the left of f, the limit's 4. As I approach 2 from the right, the limit was 1. Uh-oh, the left and the right-hand limits are not the same, so you can actually have a composite limit that doesn't exist if at the end you end up with 2 different one-sided limits and they're not the same. Okay, so I'm going to end the video. Here's a visual of the 2 problems I just did. These probably look familiar. We just did them. So you can pause and read this over. I found this to be pretty helpful reading this. I'm obviously not going to read it for you. You can just pause the video and look that over. I'm going to end this video right here. I want you to do this problem only. Wait on this for now, okay? So here's your function f. And here's your function g. I want you to find the composition f of g of x as x approaches 2. So pause that. Again, that is a you try. Practice makes perfect. So hopefully you're feeling pretty good about composite limits, and we will talk about this together.